Good afternoon. My name is Alisson Sol, and I will talk with you today about how we developed the grip and release recognizer for Kinect for Windows version 1.7. So this is an example of how to use machine learning for a real problem. And this presentation, basically, I will show you how the gesture recognition for the grip and release works. I will show you how we developed this, and hopefully you will have at the end some experience that you can reuse and take back to your companies should you decide to use machine learning for the Kinect for Windows and for other projects. Of course, this is not my work. This is the work of an entire team of people. Kinect for Windows had a lot of people working on different areas. And besides this team, we use work from Microsoft Research, the Xbox team, and others. And this presentation will focus on the practical use of machine learning. And nowadays, I work for the Bing. That was very flexible, allowing me to come here. So I know I will disappoint some of you because I will not talk about the theory of machine learning. However, you can get these slides later. And there you have one paper that you definitely should read about machine learning, 3 books, and 2 online courses with more than 20 hours of theory for machine learning. So definitely you can go and use these resources if you want to learn theory. I could not summarize all that in 1 hour. Sorry, so let's focus on what we did using machine learning in Kinect for Windows. Most of you probably know that Kinect for Windows has used machine learning before. The skeletal tracking, which is how we find a skeleton in front of the sensor and give you the joints, that uses machine learning both for the Xbox and for Windows. We migrated that code. That is explained on a paper that has been talked about before. Today, we will focus on the grip and release recognizer that we developed for Kinect for Windows version 1.7, okay? So now that we talked about the scope, let's see what is that we achieved. So it is important when you start a project to think about how is that this will work when we finish. Luckily, this is a finished product, so I can show you this. So the goal has always been to achieve this kind of interaction, whereby the sensor sees a person in front of it, then the person can just press some button, and then if we want to go and grab something, we can just grab this and move it around. This is the kind of interaction that we wanted when we started, but of course we didn't have a recognizer for when you grip or release something. How is that we would develop this? So our goal, you saw a kind of small sample that we ship with the Kinect for Windows toolkit. Our goal was to ship a lot of controls for you to be able to use the sensor without having to code a lot. So our goal was to ship, and we shipped. This is something that you can download and use today. A series of controls like this where you can press a button, and then if you want to scroll, you can just scroll and kind of move this scrolling area. So, of course, when we started, we didn't have that. So what is that we thought we would have to do? Well, we know we have skeletal tracking. So let's think for a minute. Skeletal tracking finds where the hands are. I get a window around that hand, and I use machine learning to try to find in that small picture if the hand is open or closed, or the most important, if the hand is gripping or releasing something. Okay, a lot of teams, when they think about using machine learning, they focus on the wrong problem. A lot of teams failed inside Microsoft trying to find if the state of the hand was open or closed. And they enter into discussions forever trying to decide if this is open or closed. For us, it didn't matter. What really matters is when you grip and when you release. So I don't want to go into a long discussion if the hand like this is open or closed, because I know that this is not important for my natural user interaction. And again, this is the first nugget that you can take back to your companies and your projects. If you focus on the wrong problem, you can solve it. But it will not be very useful. I have seen a lot of projects at Microsoft. No, this hand is 55% open. I cannot do anything with that. So then, okay, that we have a plan. I have a team. We have a lot of people. What is that needs to be done? First, we have to define the interface with other components. And whoever has been in this area of gesture recognition, interaction recognition knows that you can discuss forever if you do one single recognizer that recognizes everything, or if you do one recognizer that recognizes something, and another recognizer that recognizes something else, and those work together. It is almost a religion, and I don't want to discuss religion. My religion is the one of you do an individual recognizer for each gesture, and those have to work together. So inside Kinect for Windows 1.7, there are two recognizers. One recognizer is trying to recognize press, and another recognizer is recognizing grip and release. And I respect whoever wants to do a single recognizer for both. Okay? But we did define this interface. We knew that we would need to collect a lot of data, a lot of hands open and closed from different people. And we knew that we would need to create code through machine learning. Of course, at this point in time, there were some things that we knew, so we had no ignorance about that. There were some things that we had questions about, but for most of the things, we were in the second level of ignorance, which is we didn't know what we didn't know. So, but we had a process, and we knew there were 5 levels of ignorance. So the first thing that we did was this. We focused on the interface. We said, if someone will someday use this grip and release recognizer that we build, we need to be able to test it. So let's build an application, and this application we called Live Preview, that will show the result of this recognition. Let's make this application follow the interface between components that will be used by everything. And of course, this kind of application always gets assigned to the dev lead. So the poor interface here is all my fault. So basically, what this application does is it is showing you that we find the hands, we extract a window around those hands, and then when you grip, we throw an event. And when you release, we throw another event. And this recognizer here that I activated right now is the first recognizer we did. It is a heuristic recognizer that basically counts pixels away from the center of the hand. Okay? We put the developer to just go look at the depth mask, count pixels, and this recognizer doesn't work so well. Sometimes it will not recognize anything, but it allowed us to start. Jump-starting this project was extremely important. And this recognizer allowed us to start. So The final recognizer, which we developed in partnership with Microsoft Research, of course, is far better. This is the recognizer that shipped. And in the end, we will see it working inside an application. Indeed, we have seen it work inside an application. So the problem with the divide and conquer approach of software development is that a lot of teams make these block diagrams, they divide, they conquer, and in the end, they have a puzzle to assemble. So the basic thing it is, we did live preview, and the first thing we noticed is the hand position from the Kinect for Windows SDK is not stable enough. So I'll not talk a lot about this here, but there is one slide about this. We needed to solve this problem. We cannot find the hand state if the skeletal tracking is telling me that the hand is here. Second, we had to make this work on a window of 2 milliseconds. Because Kinect for Windows, the SDK, in our min spec machine, takes 15 milliseconds to find the skeleton. And you have 30 frames per second, so I have 33 milliseconds. Took 15 to find the skeleton. I came up with this number. Literally, this was the criteria. 2 milliseconds for us to find the state of the hand. Okay. And then, of course, we go and this project is assigned to the team, and only then they tell me that 3 teams before tried and failed. So Microsoft has these things. The Kinect for Windows is a very fast-paced, it was and it is still a very fast-paced team. So we shipped version 1.0 on February last year. On May, we shipped 1.5, which added Kinect Studio, which was one of the main components of 1.5. Then 1.6 had more samples, more controls over the sensor. And finally, 1.7 has this recognizer that uses machine learning to recognize grip and release. However, the recognizer, of course, needs to be ready before the other components. Because if we failed, and 3 teams before failed, we need to have time to kind of recover from this. So we decided that by the end of the sprint that we call milestone 5, which was December 19th, and the end of each of one of the internal milestones in Kinect for Windows ships to our technical adopter program. So basically, we decided that we had to have something working by that time. So then we look again. Some time has passed since we started. You remember we started with a list of 3 things to do. Now we did 1, we have 4 to do. So this is common in every software project, isn't it? So now we know that we have an interface with other components, but we need to solve this problem of hand stabilization. We need to continue and finish our data collection. We need to do the machine learning code. And we need performance and accuracy tools, because we need to measure this. Hand stabilization can take its own presentation. I will not talk about this in depth here today, but basically there was one person in our team that was assigned to this project, and he did an amazing job. Basically what he does is, there you have some illustration of the problems on the top. One of the problems is, sometimes depending on the position of your hand, it tells you the hand position is near the wrist, not exactly where you would think it is the center of the hand. And the other is, when you move your hand, it blurs. And then the skeletal tracking gives you a position of the hand that sometimes is very wrong. So he solved this problem. This is something that is going through a patent system now because really he solved very well how to stabilize the hand position. So now let's assume this problem is solved. We have a stable hand position that is always kind of near the center of the hand. I still have to collect data, isn't it? How do we do that? Because machine learning works different from your normal software development process. Typically, you have some input, and you keep trying to develop code that, when you feed that to the processor, gives you the output. But machine learning is exactly the opposite. You have samples of the output that you want, and with the input, you correlate those and create the code. So how can we do this? Well, if you seek books and the literature and those books and online courses that I introduced at the beginning, you will see that there are several methods for you to use machine learning to create code for classification, regression, grouping, ranking of data. Our problem is a problem of classification. Over time, I want to classify that at certain point in time, there was an event. I want to trigger an event. Okay? So for this, I need to do something, which is all machine learning algorithms work based on something that's called a list of features. Your problem has some features, and you will go through training to use those features to create your code. And then this code will be verified, which is basically the developers will make sure there is a number at the end, and validated, which means the testers will make sure this code creates exactly the kind of output that you are expecting. So just to make sure everybody is at the same kind of base level here, if our problem instead was to find the price of a house based on features, typically you would collect a bunch of data like this, and each column there is what we call a feature. Okay? So the number of bedrooms, the zip code, all those things are features. And in the end, you collect a lot of data, and you have the output that you want for that set of features. Now, typically, your job is to create machine learning code that, when provided with that features for one row that you still don't have that value, gives you that value. Okay? Of course, this is not exactly our problem, because this is, by the way, a regression. I don't want to go into the specifics of machine learning here, but it's very important to remember that this theory, it is a statistical theory. The algorithm will always produce a number. But you need to have a test team that will really make sure that this number makes sense. Okay? I can produce an algorithm that always returns the number 1 for the value of this house. Does that make sense? No. So, and also the value of a house may be different depending on the problem. If it is for taxes, it may be one value. If it is for you to sell the house, it may be another value. So it's extremely important to have in your team domain experts, people that will really know what is that the output of your machine learning will be used for. So we were lucky because we had such a composition of our team. So for our data capture, of course, I'm showing to many of you that have downloaded the Kinect for Windows SDK things that you know about, but you probably know about Kinect Explorer, which is our tool that just uses the sensor to showcase the depth data. Okay. So basically, we have Kinect Studio, and it shows you what the sensor is seeing. The most important for us is not the image with color, it's the image with depth. Why? Because this image is not so sensitive to illumination. If I turn off the lights here, you will still will have, because there is an infrared laser, you will still will have this depth information. Also, the depth information is something that is exactly used by the previous machine learning algorithm, the one that finds the skeleton, to find this skeleton. So we knew this information could be used. We have an application that we shipped with version 1.5 that we call Kinect Studio that allows you to connect to an application that is running. In this case, I used the only application that is running. And it shows you, even in 3D, all the depth information. What will be the features that we will use then to find if the hand is gripping or releasing? We will use the difference of depth of those points around the center of the hand when your hand is open or closed. It's very important for you to use machine learning to verify before you start if humans can see a pattern. Of course, there are problems in which you are trying to find the pattern, but here, it's very easy for you as a human to see that there is a pattern. So there must be a way to train the machine so that it can automatically create code that will find if I am gripping or releasing. Okay, so we know that our features are the depth differences. We know that we have a way to capture data, and I will show you the second internal tool that has been used in this project. We needed then a tool to tag our data, creating something called ground truth. The ground truth of a machine learning process is, what is this output that a human thinks that is correct? There are other ways to create this, but basically we had people going through videos and they tag. You can see here, those are the tags. They tag if the user, for example, just ended a grip with the right hand, with the left hand, and we, of course, recorded hundreds of videos with people going through certain interactions, and we know exactly at each point in time if they are starting a grip or ending a grip. This is the enormous database that we will use for training our system, okay? And you can imagine this is a huge investment. It's a huge investment in terms of capture. It's a huge investment in terms of tagging. It's being done right now also for the new sensor. So our process then is, I have the skeletal information, that is the output of the previous algorithm that uses machine learning. I have the depth information around the window that I extract from the depth data. And normally, I would create code. But using machine learning, what I will do is to feed this data plus the tags to some magic kind of model that will create the code for me. So those that know machine learning now already ended this presentation, but for those that don't know, let's follow through. We had all those features, the skeleton data, also the deltas, the delta meaning the difference between the position of this hand now and 1, 2, 3 or more frames ago is important, the depth differences, and if you make a small calculation, you will find that in an hour that has 60 minutes, and at 30 frames per second, I have 108 frames, 108,000 frames. Each frame has 640 by 480, so 300K pixels. Even if my window around this center of the hand is just 128 by 128 pixels, I have what? 16K pixels. Now I have to try to see if the depth difference between any of those pixels can give me the information if the hand is open or closed. So this is a large-scale problem. And that's why, of course, machine learning is something that you still don't see a lot of people doing, because this problem will demand that you pick an algorithm to look at all this data and create that code. So how is that this is done? If you go to any conference on machine learning, you will see a lot of discussion about machine learning methods. And the way I try to explain this sometimes to people is the machine learning methods are just like tools. They are tools that you can use. And of course, people get very passionate very quickly about SVM is better than decision trees, is better than decision forest, and so on. But if you will really succeed in any project with machine learning, do not focus too much in the methods. And you don't need to believe me, because if you get that paper that I recommended at the beginning of the presentation, and if you read that paper, you will see that what different methods are doing in terms of machine learning is they create different borders around your data points. So each method will create a border that is different. So a decision tree will create this kind of stair-shaped. So the SVM will create this kind of line here. And so each method creates a different border. But if you have enough data, at the end, the borders kind of converge. And that is why it's so important nowadays, this kind of word of big data, because the big data will give you the information that you need. It will make the noise disappear. So now I will go, and I beg you to just stay awake for 5 minutes, through a little bit of theory of machine learning, okay? Because I absolutely need this. I promise there is just one equation, and so this will be fast-paced intentionally. When you get the slide deck later, you can go this slowly and double-check. So we used decision forests for our code. Decision forests are forests of trees. So what is a decision tree? A decision tree is you start your code, you do a bunch of ifs, and you arrive at something that you have as a conclusion. The method that we use to create a decision tree is called this iterative dichotomizer tree, which basically is this. For each feature, for each column that is still not used in your data, calculate the information gain if you make a test based on that column. Then make a node splitting your data according to the feature that gives you the maximum information gain. And continue until you have a tree with the depth that you need. You use all the data, or you don't have more features. Of course, the first time I read this algorithm, I was thinking, this is crazy, I don't understand this. So let's go through an example. Suppose I have this data here. And this data has two features: if an animal survives underwater, or if it has flippers. And here is the output, if the animal is a fish or not. Pay attention, this is not a truth table, because if it was a truth table, it will have only 2 features times 2, 4 rows. No, this is real data that I collected somehow. So, and this is an example from one of the books that I recommended to you. So, only equation in this entire presentation. There is a theory of information that tells you that when you have several possible outcomes for a clause, the information contained in the series of outcomes is the log 2 of the probability of the outcome, and then the entropy of the system is the sum of all the multiplication of probabilities versus information, with the opposite sign because you will see. So, okay, cool. That's it. Let's see how this works. So, basically, here is the table we had. What are the outcomes? Yes or no? So the probability of this outcome here is 0.4. This one is 0.6. The log 2 of the probability is this. You multiply, change the sign. The entropy of the system when we started is 0.97. Okay? Cool. Now, suppose I make a test and split this by Hess flippers. Well, those that has flipper points to yes will come this way, and those with has flippers being no will come this way. This side, the probability of the outcome is 1. The log 2 is 0, so the entropy is 0. It's a perfectly organized system, isn't it? This side here, the probability of each outcome is now 0.5. The entropy is 1. To calculate the entropy of the entire system, I need still to consider the probability of going one side or another side. The probability of going this side was 4/50. And see that all this thing is being driven by my data, okay? And the entropy of the final system is 0.8. So making this test gives me some information gain, isn't it? However, the other test underwater is even better, because on this side, is underwater no, I will have 2 outcomes here, but here everything will have the probability 1 of outcome. I will have 2 rows going that way, and then the entropy is 0. On this side, I will have 2/3, 1/3. Double check the numbers later and send me a letter if there is some mistake. Let's use the Donald Nut approach. And basically, the outcome for the entropy is this one. So this side gives me the best information gain if I make a test at the beginning. As a result, if I want to create a decision tree for this problem, it should look like this. And you saw that just feeding this data to computers, they can create this code automatically, isn't it? So let's go. Of course, I was very fast, finished all the theory. You all passed. So I omitted several details because here, of course, my labels were Boolean. In reality, your labels may not be Boolean. You may still need to find the best place to make a test. The ground truth may have wrong labels. The trees may need testing themselves, and so on. You do this. You create a tree. You create several trees. You create a forest. Your code may still not work. Why? Because your data may be wrong, or because your model may be wrong. Your entire model may be wrong. So, and by the way, doing this is costly. We had machines with 80 CPUs doing this, and you see that the CPUs were utilized pretty well, and sometimes we would run experiments. It would take a week to get the result. So you have several of these machines running different experiments with different features to see what results. But the important thing is, in the end, it is possible to create this code. What is that you do then? And here, I will show a result that comes directly from Microsoft Research. And this application is a little temperamental. It requires that I start it directly from the folder. But basically, in the end, you create this tree, and you execute this tree for each pixel in your hand. And it gives you a classification. What is that pixel thinks that the hand is at that moment? So the red ones think the hand is open, and the blue ones think the hand is closed. So you see that? And this is early training. It's not even the best that we have. You see that when you execute this for the pixels, you can then look at the majority, and it's kind of working, isn't it? So it is possible really to use this approach in practice to create the code automatically. Wow. So we have this working, folks. It's kind of by December last year. We still need to achieve performance. The performance is not something that comes naturally because you create this code and you think, oh, fantastic. But you need to really now measure what is the accuracy that this gives me. Will it work for people with large hands? Will it work for people with small hands? Will it work for children? Will it work for adults? Will it work at 1 meter, 2 meters? Where is that it will work? Maybe it works only for the people inside our labs. So we had the lucky of having a very good test team that was able to really help us because, again, sometimes you have the wrong features. Sometimes you think something is working, and it's not. Remember, for most of humankind, we were thinking that Earth is the center of the universe, and it was working, isn't it? So your model may totally be wrong, and you may have hidden features. The house where Elvis Presley, for example, lived, you cannot predict the value of those houses where Elvis Presley, Jimi Hendrix, or someone lived just by zip code, number of beds, and so on. There is some hidden feature that you may not know about. Finally, there is wrong implementation. Sometimes we get libraries of machine learning, and they work with a few points of data. When you throw them these billions of points, they don't work really. So be careful with this thing of just because it's there, it is tested. Sometimes it's not. The challenge that we have today with machine learning is we are not focusing on creating teams like other disciplines create. So any of you that would prefer to go to surgery with team 1, it has 3 of the top surgeons of this country. So why you don't prefer to go to surgery with team 1? Because there is no anesthesiologist. It will be very painful. It may be the best option you have, but it will be painful. So what I'm seeing sometimes when I see these projects that fail with machine learning is they have the top 3 experts in machine learning of the universe. Nobody for testing. Nobody for domain expertise. So the machine learning experts are like surgeons. They focus on the science of the application, but not on how to test it. We had a very creative test team. So to test skeletal tracking, why not just put skeletons in front of the computer and try it? This is Stan, one of our testers. So you need to make sure that your tests represent the population. You cannot just, sometimes I go to conferences and I see papers. We got 11 students. Well, 11 students, they will be between 19 and 25 years old or something like that. They will all be kind of in good shape. You cannot think that represents the population. So you need thousands of data points. You need a representation of your population. And you need to be able to look at the results of your experiments and see if the results are working. We had to build tools to enable us to go and visualize what was happening. We could go and sort by distance from the sensor, sort by several criteria to see what was happening, because otherwise you don't understand. Even seeing this sometimes, as we did in 3D space, where is that the hot spots were for the hands? it is extremely important to have this domain expertise. People that were experts in user experience that could tell us, really, do not care if you don't get the hand wrong when the hand is down. That is not important. You can still ship this product if you get it correct only when the hand is clearly facing the sensor. This is information that will enable you to go ahead or not. It's very important for you to understand at least a few concepts like what is a true positive. A true positive happens when we, for example, tagged some interaction as a grip and our detector really detected this as a grip. So in this experiment, we found 129 grips, but we know there were some grips in the tagged data that we didn't get. These are the false positives. What is the false negative? It is that case where you have a grip, but you didn't trigger an event grip, or even worse, you said the user is releasing the hand at that moment. Well, that happens. When you start, you will have some of these mistakes, and it will happen. And the false positives is there is no grip at all, and suddenly the recognizer just says grip. Okay? This is terrible for interactions because whereas your hand being in the wrong position for 10 seconds is probably, or for 10 frames, excuse me, for 10 frames is not so bad. For an interaction, if you are trying to get something from here to here, and at any point in time it triggers a false positive, you drop the object or something. So our interactions need a certain minimum of correctness over time. And we were able, using these tools, to go down, see each individual interaction, why it was failing, uncover features. We learned, for example, that you need a feature which is the velocity of the hand. It is different. Your resilience to state change needs to be different when your hand is kind of more stable than when you are moving fast. Okay? So we also had to be careful with our metrics. If in 1 hour you have 108K frames, so your true negatives, which is those points in time when you have no event and no event is found, they can overwhelm all the other data because in 1 hour, typically one person makes one interaction every 30 seconds. So you have only 120 data points, really. If you put the 108,000 frames here in these equations, you will start with an accuracy of 99.9%. That doesn't mean anything. So it's better to seek other ways to measure accuracy. Okay? So the key thing to take home here is testing machine learning requires this domain knowledge. You need someone that is not just looking at the result of equations. It's really looking if your interaction is working or not. So we had this, we shipped M4, and then by December 19, we had those bugs still open in our database. Grip is inconsistent between left and right. There was an access violation when the machine wakes up for a long period of time. Coding error, this is the only one. Cursor moves downward on grip. If you are here controlling the cursor, you do this, moves downward. Grip recognition performs worse during vertical scrolling than horizontal scrolling. Okay? Palm facing grip, problematic. For some strange reason, at that point in time, gripping this way was better than gripping with the palm facing the sensor. Grip detection does not work with sweaters and sleeves. So I will not read everything, but what is that you learn quickly just by looking at the bugs? That we needed more data. Those are not the traditional bugs that you see in software development, isn't it? It is not, except for the second one, access violation. Most of the other bugs are bugs that, well, it is working, but there are these cases in which it is not working. Please find a way to make it work on those cases. So what did we do? we went and investigated. For example, why is that the right hand and the left hand are not working the same? Because depth data from the kinetic sensor is not symmetrical. Most of you obviously have been working with Kinetic for Windows, and you know this. If you get the right hand, there is a small shadow to this side, to the right side. If you get the left hand, the shadow is still in the right side. If you just mirror the left hand, the shadow changes place. So the recognizer cannot just recognize the state of the left hand by mirroring a recognizer for the right hand. See? These are the kind of domain expertise that you gain over time. By the way, this is exactly why a lot of people ask us, isn't it simple to make the sensor work upside down? No, because if you do a mirror in X and Y of the upside down image, especially because people want to put the sensor at the ceiling, the image is not exactly identical to the image that was used for the training of the Kinetic for Windows skeletal tracking. So, key messages then for you to get from this experiment. It is, data isn't the same as information. You still need domain experts that will give you those bugs that really are meaningful in that area. And that is why testing machine learning requires domain knowledge. How is that those bugs were resolved? Between December and the time we finished, we collect 10 times more data. So this is one of the challenges of machine learning. For you to get to 8% recognition, an accuracy of 80%, you require an amount of data. To get to the final, we shipped with our F score of 90%, you need 10 times more data. So we were going through a reorg internally. Our team was moving to the Xbox One work. So Microsoft Research helped us, and they did a lot of work in multiplying the data also. Rotating the data, trying to train with the data rotated, speeding up execution by skipping some pixels, and filtering the state change with a lot of very smart algorithms. And just for the benefit of time, I could show the live preview again, but I've shown that to you in the past. So let's show you how is that we use it in the end, the recognizer. So here I have a prototype that we use it to develop one of the gestures for the Xbox One. So you see here that it is showing at the corners the state of the hand. Okay? So basically shows the state of the hand. And then with this, I can start to prototype the interactions. For example, I can recognize that my arms are open. I can recognize that I grabbed. And then I can bring, for example, this is a gesture for the Xbox One. I can bring the entire screen to a tile. Okay? So this is something prototyped with the Kinetic for Windows sensor, something that you can do right now. This is very simple code. We can share the code later for you to see. That showcases exactly what we achieved. So what is that you can reuse from this experience? What is that I wanted to have as experience when I started? Your team needs to have the right mix of skills and expertise. It's extremely important that you don't really hire a bunch of domain experts or just a bunch of machine learning experts, because you need to mix the right people to get machine learning working in real applications. And you have to have management buy-in to, of course, do this. So credit to the Kinetic for Windows management for allowing us to do this. Browse through the machine learning training online, those two that I showcased and others. It's extremely important for you to learn some terminology, okay? Focus on the right problem. If we were still focusing on the hand being open or closed, we would still be there today. But because we knew that the important for our interaction was grip and release, we could finish. Implement some solution heuristically to define your interface even before you start with machine learning. Extremely important not to leave integration as a last step. And finally, have a test plan, both for your code and for your solutions. You need to have almost every single machine learning project I've seen, people need to develop tools. So have a plan for this. What if your tool is wrong? There are data sets that you can use to test your tools. So this is extremely important. So with this, I'm opening to questions. Thank you. Please try, thank you. Please try to go to the microphone for the recorded session to make your questions, okay? So.
During the session this morning, during the keynote, she used the cookbook when she waved her hand. Is any of that 8.1 Kinect related in any way, or is that?
So the question is, during the keynote this morning, there was a demo of waving the hand to use a cookbook. If that was Kinetic related, not exactly to this work of this SDK, okay? So that the Windows team has certain recognizers that they developed. Okay, any other question? Okay, so again, I will still be available, and there are 2 sessions from Kinetic for Windows tomorrow, and in one of them, it will be announced exactly how to join the program for the next sensor. Thank you.